Hello and welcome to my Physics 2211 Lab 2 about drag. The purpose of this lab is to explore the relationship between drag and the velocity of an object moving through the air. In order to explore these relationships further, I'll be taking a look at two important forces. These are aerodynamic drag, which is a force which opposes motion with a quadratic relationship to the speed times the proportionality constant, and gravitation, which is based on the mass of both objects and is inversely proportional to the distance between the two objects. So to preview my result, it was found that the aerodynamic drag resulted in a significant decrease in the acceleration of a dropped object. For the purposes of this experiment, we can simply approximate gravity to be equal to the product of mass and a gravitational constant g, which is equal to 9.81 meters per second squared. In order to find the proportionality constant b, I was able to multiply rho, the density of air at sea level, cd, which is the coefficient of drag, and A, which is the surface area of the piece of paper that I dropped for this experiment, and divided them by 2. So for this experiment, I defined the system to be the paper square, which is being dropped in the video, and the surroundings to include all other physical objects interacting with the system. Specifically, the air which produces drag on the falling paper, and the mass of the earth, which applies gravity to the falling paper. So my initial conditions are that I took a paper rectangle of dimension 0.1 meters by 0.14 meters, and I released it from a height of 0.914 meters, and I allowed it to fall to the ground. To conduct this experiment, I decided to use a tracker program and a GlowScript-based code model. So this is a video which demonstrates what the physical tracker data was based on. The resulting tracker data is as follows. As you can see, there is a increase in the rate of change of the vertical distance from the ground as we proceed towards 0, which is represented by the green line. My code is iterative. It calculates the effects of non-constant forces to model motion for each individual time step, which are synced up to match the time steps of the video. This involves two different formulas, a velocity update formula, which uses the net force to determine a final velocity over a period of time, and a position update formula, which allows me to approximate the motion of an object due to that average force. As forces are non-constant in this situation, instead of using the average as is given in this formula, we use VF. Here's the code and the results for the no drag situation, and here is the code and results for the drag situation. So here are the results for my code. The blue line is the data that was measured from the physical tracker data. The orange line is represented from when drag was modeled, and the gray line is measured from when drag was not modeled. As you can see, without drag, the object falls faster than with drag. This is reasonable as drag opposes the acceleration of gravity and should therefore cause an object to fall slower than it would in reality. However, as you can see, in real life, the object fell significantly slower than what was modeled in the code models. So the potential sources of error for this are non-representative values for a coefficient of drag and density. These are calculated or roughly estimated and therefore could be unreliable. In addition, there is likely to be significant distortion due to a single point perspective, which would cause a unrealistic representation of the difference in y values. In addition, there's a horizontal velocity component which came up at the end of the fall. This could also cause some errors due to the manual tracking. So we must also address the existence of a terminal velocity. According to the graph, only the data recorded by tracker suggested a terminal velocity. In this case, only this set of data suggested a constant rate of change of distance between the time steps, which suggests a constant velocity, which in turn suggests a net force of 0 and therefore a terminal velocity. For the simulated data, the drag simulated was likely insufficient to ultimately reveal a terminal velocity. Even if the object were to be thrown downwards, the terminal velocity would remain the same. This is because when the initial velocity downwards is set to a variety of different speeds, the velocity tends to trend to increase or decrease in order to come to an average constant downward speed, which is likely to be the terminal velocity. This is because terminal velocity is dependent only on the drag produced at an instantaneous speed and is independent of any initial speed. Thank you for reviewing my video.